I think you muted yourself.
Yes, I did. Sam, you're on. Introduce yourself.
Okay. So, hello everyone. My name is Sam Falvo. KC5TJ is my call sign. And today I'm going to give a presentation as soon as I can pull it up. It's going to be on the topic of a networking protocol, which is kind of new and unusual for me, but it's one that's near and dear to my heart because I'm actually using it. Give me a quick second here.
Yeah, we missed a bunch of what you said, Sam. You locked up there for a bit.
Okay, give me 1 second here. I'm pulling up.
I think that was just you, Dennis.
Might be.
Actually, why am I doing this the hard way? I actually have the source code on my computer. Okay, so now I got that. So now I come over here to Zoom. Click on share screen. Now you go. Oh my goodness! Now I can't select the. There we go. Close that out. Can everyone see that? It says 9P on it.
Yes, it's good.
Okay. So the protocol that I'm going to be presenting on is goes by the name of 9P. And this is a networking protocol for remotely accessible file systems. So the goals that I want to talk about is where did it come from, what applications are currently using it, what even is a file system from the viewpoint of 9P and the environment that it came from, a little bit about how it works. I won't go into too much detail because I only have about 30 minutes here. Some of the message structures, what they look like in memory and over the wire. Again, just a sampling. And then some random miscellaneous closing thoughts. And I dreadfully apologize for my CPU fan, but yeah. So 9P comes from a operating system. It's a research operating system actually called Plan 9 from Bell Labs. That's the full name of the operating system. It is more colloquially known as Plan 9. Sometimes you'll hear it referred to as 9 Front or some other variation. Usually the variation names are specific distributions of this operating system, but they all have one thing in common. They implement what's called a distributed operating system. And basically that's a system where you get the user of this environment sees a single computing experience, but it's actually implemented as multiple, possibly heterogeneous components. For instance, at Bell Labs, they implemented file servers, CPU servers, and terminals. And very often these things use different processors, including the CPU servers. And despite this, from the user's point of view, it felt like you were using a single large computing platform. The goals were to kind of take the best parts of Unix, seeing how that it was Bell Labs, and basically discard the stuff that's not quite considered the best parts. For example, the terminals were graphical, not ASCII based, right? So there was a little bit of modernization there. There's actually a whole bunch of other modernizations there, but I'm not going to talk in depth about them. Um, so the terminal CPU and the file servers, for example, they all run Plan 9, everyone. So Plan 9 is itself was a fairly small system. Um, in terms of Unix, it was a small system. When you logged in, your terminal local resources, such as the console, the bit blitter, the mouse interface, etc., they all occupy, you know, device files just like they would in normal Unix. But the way they are accessible to programs running on a CPU server, you know, in a whole different campus, for example, um, is interesting, right? So they uh, basically exported via a network protocol these interfaces so that software running on the remote system could use them as though they were local. Um, this meant that the terminal runs a file server in user space, right? Which means that we needed a well-defined messaging protocol that, you know, was essentially transparent to the kernel, and that's how 9p came about. Excuse me. After 1990, well after 1990, actually, it took a while for it to catch on, but it started to grow a little bit. For example, nowadays you will find it actually used within the Windows subsystem for Linux, so that it can handle file systems. Basically, if you take you apportion a part of your local file system, you say, I want to mount this within this virtual machine. The communication that handles that is more likely than not handled by 9p. QEMU, which is another virtual machine environment that runs under Linux, has a driver that supports the 9p protocol as well. They're actually they have actually released a newer protocol which is about twice as fast as 9p, but 9p is still supported. If you're again on Linux, if you're using the WMII window manager, WM2, I guess that's how it's pronounced. When you type in commands on the command line to communicate with it, that communications protocol is 9p. One of the other technologies that left the Plan 9 ecosystem and came to other platforms is the Acme text editor. If you work with that, it implements its inter-process communications with command line environments and stuff. That also uses 9p.
Okay, so when did it start?
I'm sorry? When did what stop? Okay, I couldn't quite catch that. I'll check the chat afterwards. But basically, so the Linux kernel, of course, has built-in support for a superset of 9p, and it's a evolution of 9p that supports all the traditional Unix file system operations. So it is particularly relevant to me because I'm using it in my FourthBox project. Basically, right now, FourthBox exists as a virtual machine. It's something that exists entirely in software, and therefore I have to write an emulator for it. But I don't want to implement hardware interfaces for each and every different type of debugging tool or whatever that I'm using for it. So I basically said, okay, well, let me use this one protocol for this. And it's convenient because when I do implement FourthBox in actual hardware, it will have a very narrow access to I/O because the number of pins on the tiny FPGA device that I'm targeting is quite small in number. So I need to have very rich access to external resources over a very narrow bandwidth, a very narrow channel. And 9p is very, very much ideal for that. So what you're seeing here is the source code to my version of type, which prints a string to the screen. And as you can see, it's five definitions. And all of the I/O follow a particular pattern where you basically transmit a message you issue the IO call. Well, let me rephrase that. You build a message for transmission. You issue the IO call, which actually encodes it into a packet and sends it, waits for the response, and then decodes that, and then you process the received message. And IO call is a single word operation that's used quite frequently. I won't get into its definition here. Anyone who's interested, it can reach me via email afterwards. But basically, I just wanted to go over this code because, as you can see here, basically I'm building a command structure, or a structure with a command code of twrite. I'm telling it which file ID to use, and I'll get into those a little bit later. Which terminal? Sorry, that's not a file ID. The term FID is the file ID. This is for tracking multiple concurrent IO operations, which I actually don't use. So I just pick a random arbitrary value for that. And so basically, once I'm done with that, I then place the string embedded at the end. And so that's how the message gets built. And then once the response gets back, I do some basic error checking, very basic. I check to make sure that the response is the R write option, for example, and that the tag value matches. Again, I'm not going to go into too much detail here because of limited time. But so what is a file system from 9P's perspective, or from Plan 9's perspective? And most people think of, oh, I'm going to mount this disk for data storage, because that's what a file is, right? It's a file of bytes. Well, it was never really about that, and in Unix, and it unfortunately it kind of became that over time. So with Plan 9, they really wanted to drive home the idea that it's the interface aspect of the file system that's what's important, right? So in Plan 9, the file system is indeed a place for storing files, but it's also a hierarchically arranged key value database. And because of that, they treat it as a user-facing interface, one or more resources, right? If you're familiar with Linux, the /proc file system is a good example, right? Let me quickly demonstrate that. Yes, I can. Okay, so if I do /proc and I do a listing, whoa, we get this, what is this mess, right? So we get some information about files, we get information about interrupts, we get, of course, anyone who's familiar with Unix will recognize these as the currently running process IDs, right? And just for grins, I'm in 5437. So if I do 5437, right? So this is all the information that's relevant to this particular process, which is the shell. For example, I can get a copy of the command line, which, as you can see down here, just says bash, right? That's essentially how, if I do maps, this is the memory mapping. This is all the libraries and modules that are currently mapped into the shell's process address space, and so on and so forth, right? So you can actually do a lot of deep introspection with this. And none of those is actually a text file. These are all constructs that the kernel already has in memory. It simply exposes it as a file. And not all files are readable and are read-only. Some of them are read-write, right? So you can actually change things. The /proc/pid/mem file, for example, you could actually modify a process's memory space if you really wanted to. Not that I recommend you do that, but and honestly, this is not a new idea, right? Obviously, with Unix, we have everything as a file. That's where that idea came from. But it was shortly after that, it was independently arrived at by Commodore. If you'll notice that everything in the Commodore environment, everything is a GPIB device, right? And then finally in Plan 9, they refined it to everything is a file system instead of everything is a file. So how does it work under the hood? There are several steps, some of which are only executed only once. But you start by negotiating a version that is in common between you and the remote server. In this case, I'm telling it I want version 9P 2000, which is the original released version of 9P. And if I can't get it, then I just error out because that's the lowest version that exists. Like I said, the Linux kernel supports a later version, which I believe is 9P 2000.L. And so, yeah, that's essentially the first thing that you do is you establish a version that's common between both the client and the server. After that, you attach a file ID to the server's root directory. Now, a file ID is any number unique on your connection that you choose. Strangely enough, it is not something that the server chooses. You actually choose this number for your own benefit, which is why I can get away with just picking numbers at random. Yeah, so the next step is you attach to a root directory, and basically that file ID refers to essentially / on that remote resource. But after you're done with that, you then need to walk to the desired resource on that file system. And that's what I'm doing here. In this case, I'm walking to what would basically, ooh, that's a wrong, poor choice of colors. Basically walking to /0/term ASCII in this particular example. And you'll notice that there's no slashes in the name. They're actually passed as separate elements, which is awfully convenient for Forth because it saves me the trouble of having to parse. Eventually I'll be needing it, but I'll cross that bridge when I get there. Finally, you open the resource. So the file ID is basically set to a particular file name at this point, but it's not actually open. So now you actually go through the step of opening it, which does the security checks and, you know, making sure that you're not opening an exclusive resource multiple times, etc. Also, this IO unit, part of the message, which you'll see in a little bit, tells the establishes to the client the largest unit that you can read from a file or write in that case, which is convenient. In my case, I'm eventually going to target a CPM machine, so my largest IO unit is 128 bytes, which means that if I have like a 4 megabyte file and I pass it a 4 megabyte buffer and I say, you know, write this entire chunk of 4 megabytes, it's only going to write 128 bytes. So it's good to know that up ahead of time so that you can sit there and you can iterate in a loop how many times you want to need to send. And then finally, you just read and write. And once you've established an open file, reading and writing over 9P is about as simple as accessing SD cards, because the interface at that point essentially becomes isomorphic. You basically have a read command, you tell it where you want to read, and then you basically wait for the result to come back. Or you give it a write command and you tell it where to write, here's the stream of data, and then you wait for the response that says, yep, I'm done. So in this case, once you've gotten this far, 9P is actually really convenient to use. And there's other stuff that I haven't implemented yet, such as stat and wstat. I don't think I will implement these because they're not relevant for my immediate needs. Clunk is a command to close a file, but it also releases a file ID. So it's a little bit more than a normal close, I guess. That's why they changed the name to Clunk. Flush is interesting because it cancels an outstanding IO request. For example, if I want to open up a mouse controller interface and I issue a read on it, but I haven't moved the mouse yet, according to 9P, my read has to block because the data doesn't exist yet until I actually move the device. But if my application is going to, exit, for example, I need a way of canceling that pending interaction. And that's what the flush command is for. Create, of course, creates new files or directories, and then remove deletes them. And that's it. If you add all that up, it's basically just 14 commands and responses. And that's all you need to implement to have a productive remote file system interface. So over the wire and in memory, this is kind of what some of the structures look like. And you'll notice that there's a lot of structural similarity between them. They all start with a size field, which specifies how many bytes in the message exist. You have, and these numbers in the brackets tell you how big the fields are. So in this case, these are all 32 bits wide because they're 4 bytes long. We have read, write, walk, and clunk in this example. These are the transmit messages. These are the streams of bytes that you send to the remote server. Tags are used so that you can support multiple outstanding I/O operations. For example, going back to my mouse interface, I can issue a read on that mouse file. I can also issue a read on a keyboard file, but at the same time, I can also issue a read on a disk file. More likely than not, the disk file is going to return data long before the keyboard or the mouse port will. And so therefore, I need a way of saying, oh, the result of this read operation belongs to the one that you asked me to read the disk file from. That's what this field is for. It allows you to disambiguate and demultiplex I/O operations. And usually, most operations take a FID or a file ID, and you are free to assign any 32-bit value your heart desires for these. They're actually bound on the server side to a specific resource by either the attach operation or by the walk operation. But I won't get into those because that took me the longest to figure out, and I would imagine it would take me the longest to explain as well. Read and write, of course, the offset specifies where in the resource you want to read and write if it is a persistent resource. If it's not persistent, like a device file, for example, more often than not, this field is 0. And a count of how many bytes you want to transfer. 9P allows you to transfer up to 4 gigabytes per transaction. You very rarely have support for that large of an I/O unit. And then, at least in the case of writes, you stream the data at that point, right? And you specify a 4 byte. This count field specifies how long the data field will be. The corresponding results are here. These are the reply messages. And basically, you'll see, there's these QIDs I'm not going to really go into. I thought that I was going to, they basically represent resources on the server that uniquely identify them somehow. But explaining those is probably about as difficult as explaining how, the walk operation works. And speaking of walk, here's the new FID field that I was telling you about. Basically, you start with the root FID, and then you specify, oh, here's this new FID that I'm going to specify belongs to whatever resource is named here. Yeah, this is probably the most complicated part of the protocol. But once you have that down, everything else is pretty easy. So 9P for a remote file system protocol is very simple. I implemented what I currently have in about 2 kilobytes of code in the virtual environment in ForthBox. The corresponding lines of code in the emulator's server is about 1,000 lines roughly. That includes all the boilerplate. That includes data structures that I need to keep things in order and so on and so forth. The actual message handlers are actually fairly compact. if you go back and you add up all the bytes that correspond to a read, both the outgoing message and the incoming response for both reads and writes, it turns out that it's about as link efficient as rapid I/O and hypertransport. This kind of surprised me. Basically, to transmit 1 byte, you need to be able to transmit about 19 overhead bytes. But if you also want to transmit 256 bytes or 256K bytes, then you're talking about 19 bytes of overhead, right? So as your as your payload size goes up, your efficiency starts to go up as well, and the efficiency is basically the same as that as rapid I/O. That's actually kind of surprising to me, and even opens up, the thought experiment. What if instead of using rapid I/O fabric on a motherboard, why not use 9P at the hardware level? So that's kind of an interesting thought. I'm not sure that I would go that route, but just something to play with. And in terms of implementing a inter-process communications channel that is scriptable and so forth, at least on POSIX environments like Linux, it is the first real competitor that I've seen to the scriptability that you find on Amiga OS using AREX. But that is perhaps a topic for another time, because I see that I'm just about out of time. And with that, thank you very much. I think I've got time for exactly one question, and then anyone else wants to reach out to me can please do so by email, which there's my email address right there, or you can reach me on the mailing list. Thank you.
Hey, that was a great presentation. I was really interested, and I didn't know about 9P, so thank you for sharing with me. I knew about Plan 9, but I didn't know about 9P. And I was just curious, you said that you were connecting to a CPM machine. Can you go just a little bit more into what your goals were for implementing this?
Yeah, so I'm basically making a very small computer, homebrew, but the channel that I'm building it with is very, very narrow. I've got basically 12 I/O pins that I can use to communicate with the rest of the output, the rest of the real world, essentially. And
You're doing this on like an FPGA board or something? Is that the issue?
No,
yeah.
Okay. It is an FPGA board, actually. Let me see here. Probably it would be better to show pictures if I can. But of course, when I pull it up, yeah, I'm not.
Well, I was mostly just confused by the reference to CPM. So if you can.
Yeah. So I have a computer at home called the RC 2014, and I built for myself a plug-in card called the B Explorer, and that card. Well, here, let me. I'll send you the link to that on chat. Now I have to here go over to the chat. Okay, so I posted my Hackaday link on there, but if you scroll down on that page, you're going to see a plugin card that I'm currently using for FPGA development for basically a video card for that platform. That uses a tiny FPGA BX, and as a result of that, I only have like 30 pins of usable I/O, which is enough for the video card. But the processor interface is only about 12 bits wide, right? You've got register selects, you've got chip selects, and then you got the 8-bit data bus, and that's essentially it. And so what I wanted to do as a secondary project, just for fun, really, was to implement a homebrew computer on that FPGA. But because I can't afford ROM or anything like that, I need a way of streaming data into the processor from some other device. In this case, the Z80 that runs on the RC 2014, and that machine runs CPM. So I thought, okay, well, if I can build a a purpose-built interface to do that, but I'm also going to need access to a keyboard. I'm also going to need access to file storage or block storage, as the case may be. So how do I do that? Using that.
You do it later. We've got to move on. My apologies. Two comments I wanted to make about the chat. One is be circumspect in what goes there, because we do record the chat and post it. Also, when you post something to the chat for posterity, be sure to label it, because there's no correlation between the actual Zoom and the chat. There are no timestamps or anything, and it's tedious. So, Sam, if you want to tell the chat what hackaday.io/project blah 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 is in the chat, that would be great, so that somebody can come along later and make sense of what that was about. Dwight, you're up.